Hello, Dr. Ashraf. My name is Soroush. Me and my friend Saeed are presenting our project for the Advanced Power Systems course. Our project name is Performance Optimization of DC-DC Buck Converters in Solar and Energy Harvesting Applications using a Linear Quadratic Regulator, or LQR.
Hello, Professor. Thank you for listening to my presentation. My name is Saeed Shafiee. This study aims to improve the efficiency and stability of DC-DC buck converters used in solar and ocean energy systems by adding a linear quadratic regulator (LQR) controller. Buck converters are important in renewable energy systems. However, the performance of these converters depends on the control method used. The traditional PID controllers are not always effective in dynamic environments like solar and ocean energy. The LQR controller is introduced as a solution, as it can provide better efficiency, stability, and faster response. This research includes a review of existing methods, system modeling, designing the LQR controller, running simulation in MATLAB, and showing the result of using LQR controller in energy harvesting. PID controllers are commonly used in renewable energy systems like solar and ocean energy because they are easy to implement and cheap. However, they have problems in environments where conditions change rapidly. In solar energy systems, for example, the amount of sunlight can change quickly due to the passing clouds, which makes it hard for PID controllers to adjust in real time. This causes instability and reduces the efficiency of energy harvesting. And in ocean energy systems, PID controllers struggle with the unpredictable changes in wave patterns, leading to similar issues with stability and energy losses. This highlights the need for a more effective control strategy that can handle these fluctuations while maintaining optimal energy conversion and a stable output, which the LQR controller can provide that. In ocean energy systems, wave energy converters often use adaptive control techniques to deal with the changing nature of ocean waves. While these techniques can adjust to wave variations, they don't guarantee optimal performance or stability. Adaptive controllers may work well for small changes, but they can't always manage the larger and more rapid shifts in wave patterns. This creates a gap in achieving the best possible performance in ocean energy systems. The LQR controller solves this problem by being more robust and efficient. It can make precise adjustments to keep energy conversion at its best, even in fluctuating ocean conditions. DC-DC converters are essential in renewable energy systems, but they often struggle to deal with fluctuating input conditions, like changes in solar irradiance or ocean wave intensity. These fluctuations make it difficult for traditional control methods such as PID to maintain steady performance. This shows the need for better control strategies that can adapt to these changes. The LQR controller offers a solution by setting a new standard for efficiency and reliability. It works by minimizing energy losses and ensuring stability, providing a more effective and robust approach uh, compared to traditional methods in managing fluctuating renewable energy inputs. This study shows the potential benefits of using the LQR controller in solar and ocean energy systems. Through a comparison with traditional control methods like PID and adaptive controls, it demonstrates that LQR controllers improve efficiency, stability, and response time. The results show the LQR controller can adapt to dynamic and changing conditions much better than older methods. This research not only introduced a more advanced control method for today's renewable energy systems, but also sets the stage for future studies in the field. It opens the door for more research on control strategies to further improve the efficiency and reliability of renewable energy solutions in the future.
Following Saeed's talks, I'm going to talk about LQR controllers and I'm going to present a brief theory. So, to fill the gap in the research we presented, we're going to introduce the linear quadratic regulator, which is a model that uses optimal control to minimize a cost function and represents dynamics and operational characteristics of a system. Here we have the cost function formula, which x is our states, u is our input, and q and r are our weight matrices. Q should be a semi-positive definite, and R should be positive definite. And these constraints put limits on our cost function. However, determining the right R and Q will choose our strategy for our optimal control and finally our control law. In this slide, I'm going to talk about the integration of LQR controllers and how they're going to be implemented in our system. So in the formula we see, the formula is a control law, which is an answer of the Riccati equation. And like P is the answer of the Riccati equation. R is the same matrix we had in the last slide. And X is our states. So U give us the input for the control signal in which the cost function J is minimized. And this control law ensures the efficiency in our operation, and this makes our LQR algorithm optimal. In this slide, we're going to present a comparative analysis of the three proposed ways. We can see that for PID controller, we're going to have an efficiency of 85% and a relatively high time response, but a moderate robustness. And we can see that because of its simple equation. It just needs a few multipliers and some equations. It's really simple to implement, but for our method, we're going to move to better solutions. So we can see that in adaptive controllers, our control law, ut, is a function of the error. So we're going to have to find the formula for the adaptive gain. And we're going to have, it's proven that it has higher efficiency of PID, and it's a very robust system. However, LQR, because of its optimal nature and the control law coming from the Riccati equation, has the highest efficiency, the best response time in these options, of course, and the best stability. This slide shows the preliminary and the simple circuit of a buck converter, which we are going to design a controller, an LQR controller for. So we all pretty much know how buck converters work, but I'm gonna explain briefly. So this has two main states. In the on states, the S switch is activated and the input voltage Vs is linked to both inductor and diode, leading to a flow of current through the inductor and into the load. At this point, the inductor current increases slowly, and the diode is reversed bias mode, which blocks any current from passing it through. So in the on state, the FD diode is open circuit. In the off stage, the S1 switch, which could be a MOSFET, it's turned off and the input voltage is disconnected from the whole load and the inductor. So the current flow is stopped, and at this point the inductor discharges its stored energy to the load and supplies current to it. During this process, the inductor current decreases linearly, and also the diode becomes forward biased and allows the current to flow from the load back to the inductor. In this stage, the capacitor, which is charged in the on stage, will keep the load's voltage from dropping very high. So our challenge here is to send a control signal to the S1 switch to be able to stabilize this circuit, especially when the Vs, the input voltage, is fluctuating. Our research shows that LQR is a very optimal and efficient way to control S1 switch. In this slide, we can see the MATLAB Simulink blocks and the simulation of a modeled buck converter into state space equations. And we can see the closed loop linear quadratic regulator implemented with the blocks. And on the right side, we can see the voltage operating very efficiently with the closed loop LQR. To better implement our design and simulation into practice, we wanted to simulate with PSPICE. We want to simulate our circuit with PSPICE. However, we couldn't stabilize our circuit in practice, and we couldn't move to the design stage because time didn't allow us to work more on our project. So we're gonna stop here for project B, but still the interest remains, and we're gonna continue further. This slide shows our results and analysis for LQR controllers for applications in solar on ocean. And we can see the increased efficiency, reduced energy loss because of our optimal approach. We can see improved stability, and the system shows that the fluctuating input shows that our system remains stable on the various conditions. And also we have faster response time in compared to PID and adaptive. In the mentioned applications, in solar energy, stable output voltage and minimal overshoot is very important, which LQR can implement in the real world. For ocean, the effective handling of stochastic nature of waves and the ocean, and with maintaining stability and efficiency is very important, which LQR can accelerate in both approaches for sure. We hope in the future LQR is considered in the controllers, and we wish we could have more time to work on our project and propose a better design to stabilize our approach in real practice. Thank you for listening to our presentation. On behalf of my friend Saeed, have a great day.